Take a moment and draw your picture in for the graph of f of x equals 1 over x. We've already explored what happens to the output values of this function as x approaches positive infinity and as x approaches negative infinity. Now what we want to talk about is what happens to this function as x approaches 0. So I'm going to get another color here. Imagine approaching the place on this graph where x equals 0, approaching from the right-hand side. Whoops, that wasn't a very good trace. But what happens to the y values of this function as my x value gets closer and closer to 0 coming in from the right-hand side? Well, you can see that those values, you can think about where they come from. I'm going to have 1 over 0.1, 1 over 0.0001. You can imagine with a 1 in the numerator and a number very close to 0 in the denominator, the result of that fraction, the output is going to be quite large. And we can see from this graph that in fact the output values grow toward infinity. If we tried approaching the place where x equals 0 from the left-hand side, we see that those y values, those outputs, approach negative infinity. So I have these two limits here. And what we notice is that what's exciting about this graph, one of the things, is that there's a vertical asymptote right there where x equals 0. And that actually leads us toward an official definition now of what a vertical asymptote is. So there's a place for this in your notes. F of x is going to have a vertical asymptote at x equals a if the limit as x approaches a from the right is equal to positive infinity or to negative infinity, or if the limit as x approaches a from the left is equal to positive or negative infinity. And as you can see here, we even have two of those happening. The limit from the left-hand side was negative infinity. The limit from the right-hand side was positive infinity. There's still a vertical asymptote. So any one of those four cases could occur to make a vertical asymptote in our graph. So just notice there's a note in the box, the bottom of the box at the top of page 4, about how this number, infinity, is not really a number. It's certainly not a limit. So to say that the limit of a function as x approaches a certain value is infinity is to say that that limit fails to exist. So it would be correct to say that the limit as x approaches 0 from the left of 1 over x does not exist. But that's different from saying that just because the limit does not exist that there's a vertical asymptote. So in order for a vertical asymptote to be present, you're going to need that limit to actually equal positive or negative infinity. So here we're going to practice a little bit of sign analysis, that's S-I-G-N analysis. I would expect that maybe you've seen something like this a little bit in your pre-calculus class. We want to try to understand what the graph of this function might look like. I don't need anything too specific, but this gets to an idea that's going to be really important to us later on. So here I've asked you to find the vertical asymptote of this function. My whiteboard, there we go. So what makes a vertical asymptote? So if you're going to think about it algebraically, we know what makes it happen because we just talked about a definition. But if you think about it algebraically, what value of x could my graph never ever touch? Well, it's going to be, in the case of a rational function, any value of x that makes the denominator of that rational function equal to 0. So you can see that sort of my first step toward answering this question here is I'm going to factor my rational function so that I can understand it a little better, and I'm going to notice that any time my denominator, so 2x plus 4, is equal to 0, I'm going to have something really exciting. If that x plus 2 factor had canceled with the numerator, I still have something exciting, but it won't necessarily be a vertical asymptote. But here, I had no canceling with those, none of those factors canceled, and I can solve 2x plus 4 equals 0 to find that I'm going to have a vertical asymptote at x equals negative 2. Okay, I'm very sorry to report that my original slide has a bunch of typos. Everywhere that there was a 2 over here on the right-hand side, it really should have been a -2. So I've gone through with my little blue pen and put the negatives in front of the 2's. I hope that doesn't throw anybody off. If there's anything I can clarify, I'm happy to clear it up in class tomorrow. So I've been asked to describe how this function behaves to the left and to the right of any vertical asymptote, and I know I have one vertical asymptote at x equals -2. So what I want to think about is, what if I were going to use x values that are just a little bit bigger than -2? Those are numbers to the right of x equals -2. So I have this factored version of my function that's going to be very helpful. And so think of a number that's a little bit bigger than -2. So like -1.9 is a little bit bigger than -2. So we're going to imagine substituting in this value, -1.9, everywhere we see x. But it's not so much interesting to us what the exact value is. We're interested in whether the results are going to be positive or negative, and whether they're getting bigger or getting smaller. So if you imagine plugging in a -1 for x, sorry, -1.9 for x, this term is going to turn into -1.9 minus 1, which is -2.9. So -1.9. I'm going to have, so that factor that was x minus 1, when I plug in a -1.9 for x, the result is a negative value, -2.9. What happens when I plug in -1.9 to this factor? I'm going to have -1.9 plus 1, again, negative. That's a negative sign inside parentheses, in case that's hard to read. And down there in the denominator, this is where it's interesting. If I'm going to use a number just a little bit bigger than -2, I'm going to have this 2 here that's multiplying, and then -1.9 plus 2. Well, -1.9 plus 2 is 0.1, which is positive. And I'm going to have that 2 multiply, so I'm going to have 2 times 0.1, which is 0.2. What's really interesting to me is that that result is going to be positive. So if I think about that result, f of -1.9, so my function's value, when I plug in numbers that are very close to, well, pretty close to -2, but a little bit to the right, I'm going to have, if you think about what this means, in my numerator, there's going to be a negative number times a negative, well, a negative value times a negative value, all divided by a positive. Well, negative times a negative, positive, divided by positive, still positive. That tells me that f of -1.9 is positive. I don't really want to write equals positive. Let's see, I could write is positive. And I know if there is a vertical asymptote at x equals -2, then as I approach from that right-hand side, I'm going to either approach positive infinity or negative infinity. I'm going to conclude that as I approach x equals -2 from the right, my y values will approach positive infinity. So I would say that the limit as x approaches -2 from the right of f of x is positive infinity. So if your infinity is positive, you don't have to put the plus sign in front of it. But you could, that'd be fine too. Let's take a look at the other side of that asymptote. All right, I have the same typo here, so I've put my face in front of the, mostly in front of the wrong math, and replaced your 2's in that final statement with -2. So let's see if we can get this cleared up. If I want to figure out how this function, f of x, behaves to the left of the location of my vertical asymptote, I'm going to consider plugging in numbers, substituting in values for x that are smaller than -2. That means to the left of -2 on the number line. So you could think of the number let x equal -2.1. That number is smaller than -2. It's to the left of -2. So I could Remember, what's interesting to me is not so much the exact value of f of negative 2.1, but more the sign of that value. So imagine substituting negative 2.1 in for x. So start with this factor up here. In the numerator, I'm going to have x minus 1. I'm going to replace the x with negative 2.1, so negative 2.1 minus 1. A negative result. What about negative 2.1 plus 1 to evaluate the second factor? Well, that's going to be negative 1.1, which is still negative. It's going to be different from the last case. Now, when I substitute in negative 2.1 for x in that denominator, I'm going to have 2 times the quantity, negative 0.1, which is going to give me a negative result. So those are, to clarify, negative signs or subtraction symbols in negative signs is better inside parentheses. So if I were to evaluate f of negative 2.1, my numerator would have a negative value times a negative value divided by another negative value. Well, negative times a negative, positive divided by a negative result. So I would say f of negative 2.1 is less than 0. That's another way of saying f of negative 2.1 is negative. So I would conclude, since I know as I approach negative 2, in this case I'm approaching from the left, I'm either going to approach negative infinity or positive infinity because I have that vertical asymptote there. So I will conclude that as x approaches negative 2 from the left, f of x approaches negative infinity. I would write that as the limit as x approaches negative 2 from the left of f of x is negative infinity.